Good evening, Professor. I am Imtiaz Ahmed Shah from iData Lab, Professor Kim Jong-un, as enrolled in third semester of Masters. I want to give presentation of MMIC technology books from chapter 1, that is review of MMIC technology. These presentations for my coursework about MMIC applications, which I want to need to submit this presentation of our Professor Nami M. King. So this is my contents and table of contents I want to discuss in these presentations. That is introductions. First of all, I want to say the introduction of MMIC technology. Here I will discuss how MMIC technology comes from MIC technology, then materials and device of MMIC technology. What are the materials? In this chapter I will discuss some materials we are used for MMIC technology, and then I want to say about MMIC active device, that is what are the active device we are using in MMIC technology, and then I want to discuss some passive components of MMIC technology. Last of all, I include some reference where I collect this data, and also put some reference from these books where the data is collected for these books. So first of all, I want to say the definition and introduction of MMIC technology. So before telling before telling about MMIC, first we can talk about MIC technology, that is microwave integrated circuit. There are three types of circuit elements that either are used in chip form or are fabricated in MIC, that is distribution transmission lines. Distribution transmission lines, we know microstrip line and coplanar waveguide line, strip line. Another one is lump elements, that is resistance, inductance and capacitance. That is another. Last one is solid state device. That one is more important in our MMIC technology, that is FET, BGT and diodes, transistor. Two types of MMIC, two types of MIC, microwave integrated circuit technologies are there. That one is hybrid microwave integrated circuit, is MIC. Another one is monolithical microwave integrated circuits, that is our MMIC. So we first we can say that where MMIC technology, this type of word comes, monolithical, that is it comes from the Greek word monos, that is means single, and another word that is lithos. Lithos means stone. So thus a monolithic integrated circuit is built on a single crystal. A monolithic circuit or MMIC are a type of integrated circuit that operates in a microwave frequency. We know the microwave frequency is about in gigahertz, that is 300 gigahertz to 300 megahertz to 300 gigahertz. These devices basically performed function as a microwave mixing, power amplification, low noise, LNA, low noise amplification, low noise amplifier, high frequency switching, that are used in RF and microwaves communications. MMIC are dimensionally it is so less, and in millimeter, that is in also microwave range, that is around 1 millimeter square to 10 millimeter square, and also mass produced, which has allowed a prolifications of high frequency device such as cellular phones. These makes easier to cascade the MMIC and external meshing networks. Here I mention the frequency range which are used for our communication, mobile communication, satellite communications. All are wide band frequency. All are high microwave frequency also. So then I can discuss about what is the history of MMIC technology. Origin of MMIC technology, in 1964 government programs at Texas Instrument, they first introduced then MMIC technology. It is MMIC technology shares a common root with silicon monolithical and digital IC technology. Silicon integrated circuit technology had been launched in 1964 programs, and the program's objective was to build a transmit and receive modules for a phase array phase array radar antenna. However, the results are disappointing due to the poor semi-insulating portion of silicon. Later, in 1968, Mehal and Okar fabricates an integrated circuit and composed of a 94 GHz from front-end device, that is receiver using a semi-insulating gallium arsenide substrate, and Schottky and Zahn diodes as active device. And the last moment in 1976, Pengali and Tuner utilized a MOSFET, that is metal semiconductor field effect transistor device, that on gallium arsenide to create high frequency X band, that is almost 10 GHz range amplifier. And in 1988, ARPA initiated the MMIC programs as substantial research effort. This endeavors results in a various communication commercial application like DBS, TV receiver, automotive solutions, wireless network, LANs, office and personal cellular communications. Actually, monolithical circuit, from the here word we can understand that monolithical and microwave single stone so much is narrow size, and microwave range frequency we are using that microwave frequency that are used in that technology MMIC. Now I want to discuss here there is a comparison where we have some comparison between MMIC and hybrid MIC. Hybrid MIC is the latest and update on MMIC is first introduced, then later we can introduce hybrid MIC came. So here I want to some mention what is the advantage and disadvantage of MMIC. So advantage, first of all, we can say it is low cost and size is so small, and high reliability. All the components are fabricated and simultaneously there is no solder joint. Improved reproductive and performance. And in case of disadvantage, some disadvantages also are available. So this is processing difficulties. It makes processing is so much difficult. Inherent resistive losses, there is a loss are there, and low yield because of effect of component tolerance and distinguishes. Also small size limits heat dissipations. Also there is a heat dissipation is happening there, so much heat is generated. Then another updated technology came, that is hybrid MIC. Its maximum have the advantage, some low amount of disadvantages are there. First of all, the advantage is cost is so low and simple circuit. Size can also be so much small, and multiple substrates are used in the passive component with embedded as in a passive components, and can choose the best transistor possible from range of manufacturing companies. Time required for layout and construction test is comparatively small, and on disadvantages are there and does not have a good reproducibility and reliability. Hands tuning and bonding device and components together. So some applications of MMIC technologies I mentioned here. It have lots of applications in communications, homeland security, scanner, imaging and sensor. Among them, military and space and civil include in this PPT. So this one is the major used in MMIC technology field, and they used as a major technology field for MMIC technology. MMIC technology is suitable for space and military communications, and that meet requirements of shocks, temperature conditions. And there are major factors the success of MMIC development in microwave solid state device. That is military purpose came first. That is adaptive phase array radar and synthetic aperture radar are used MMIC technology. Smart munitions and decoys are also used for MMIC. Electronic warfare, remote sensing and altimeters. And another one is most important, this is also space. In satellite communication we are using this MMIC technology. Satellite and radiometers and astronomical field also we can use. Synthetic aperture radar, we also use the MMIC technology. And civil means wireless communications, LANs, Bluetooth, RFID, that one is used in market. market, and medical equipment, biomedical applications also we are using fiber optical communication systems, we are using MMIC technology. So from we can see that lots of applications are there in modern technologies we are using on the benefit of MMIC technology. So materials, some materials are used in MMIC technology. Materials for monolithic microwaves integrated circuit, that is first on we need to introduce about the substrate materials, that is gallium arsenide, silicon, berylliums, aluminiums. These are most among them, so we are using silicon and germanium. And some these materials have and a substrate of a monolithic integrated circuit is a piece of substance in which the electronic devices are built. The ideal substrate materials should have a following characteristics. These characteristics or properties we mentioned here: electrons mobility, resistivity, permittivity, thermal conductivity, wafer size, wafer cost, how much the cost of the substrate, thin plate, that means wafer, energy band gaps also need to mention for the properties. Among them we already mentioned in a tabular form, that is silicon, gallium arsenide, gallium, silicon, gallium, silicon carbon, gallium nitrate. We mentioned how much effect on circuit here, gain, which one is more effect on circuit design. Some parameters I put in here, so from that we can use here. It is costly, this type of energy band, it is takes so much costly for in case of circuit. So we can go next slide. That one is the active device of MMIC technology. Active device, MMIC technology active device is first of all we can say the active device, most active device is gallium arsenide, MESFET metal semiconductor field effect transistor, that is gallium arsenide. And the most gallium arsenide MESFET device are operate in a depletion mode. Depletion mode, we know the MOSFET have two mode, enhancement mode and depletion mode. So we are using most of the cases is depletion mode and requiring negative voltage. In higher depletion mode we are requiring negative voltage to control the gate bias. And enhancement mode mode device with a shallow channel only require a single polarity supply. And the advantage of gallium arsenide over silicons are its high saturation electron drift velocity and lower field mobility. Electron mobility is so low, and which increase the speed of the device, and its high resistivity of our passive components. Here the cross sectional view of the gallium arsenide metal oxide semiconductor, that is, we know the some field effect transistor we have 3 port, that is drain, source and gate. Actually gate is control the voltage source between drain and source. Also there is a active layer between source and drain, in between the gate, and there is a buffer layer. In the last layer we put some substrate for gallium arsenide, we are used for gallium arsenide MOSFET, that's why. So basic schematic of this MOSFET here in this figure we understand, and this is the equivalent circuit of MOSFET. Here I already previously told the gate is control for drain, control between the voltage of drain and source. That's why I put here drain, and here this side is gate and this side is drain, and in the bottom place I put the source. That means we can control from that gate voltage, we can control some voltage between drain to this source and drain to another this line source. So another active device is gallium arsenide HEMT. That means HEMT transistor means we can understand the high electron mobility transistor. It is the abbreviation form of HEMT. HEMT transistors are able to operate higher frequency than ordinary transistor, up to millimeter wave frequency, are used in high frequency products, and high electron mobility transistors are also known as high electron mobility transistors, and heterostructure of FET also, heterostructure FET, HFET also we can told. uh, so high electron mobility transistor have some characteristic, that is heterostructure. Also it is heterostructure transistor which deliver high electron mobility. It exhibit the lowest noise figure and high gain, but it can be poor choice for low frequency applications. Always we need to remember, we can use, whenever we can use high electron mobility transistor, that should be for use for a high gain frequency and high gain, and so whenever we increase the frequency, our gain should also increase simultaneously. It is just like a proportional relationship. Another device that has become increasingly attractive in alternative indium phosphate and based on HEMS for low noise and low power applications in the metamorphic high electron mobility transistor. It is the most gallium arsenide device structure. Here, this is the cross-sectional view of the high electron mobility transistor. Also, it is in the bottom layer is using gallium arsenide substrate, so that's why its name is gallium arsenide high electron mobility transistors. This is also transistor, already we have know the 3-port source drain gate. So this one is negative gallium arsenide. This is pulse doped. We doped means we are mix another components for in this high electron mobility transistor gallium arsenide, that is aluminum gallium arsenide and undoped indium gallium arsenide. This is buffer layer. We can control both of the above layer and substrate with the buffer layer. And this is the as I earlier told, in high electron mobility transistor gain is more important. So also there is a drawback comes noise figure also here we need to show. So this is the comparison and gain and noise figure I give you in PPT. So this is the high gain. Here from that line you can understand the gain, and from the below line we can understand the noise figure value. So another active device is active device MMIC, monolithic microwave integrated circuit, that is gallium nitride in high electron mobility transistors. So gallium nitride and gallium arsenide, these two are used in maximum case in our monolithic integrated circuit. So advance in silicon, germanium and heterojunction bipolar transistor HBT technology resulted in an impressive increase the high frequency performance during the last decade and extending the address application frequency in millimeter and sub-millimeter wave bands. So aluminum gallium nitride has a higher frequency range and band gap than gallium nitride, and silicon impurities donates the electrons to the crystal. These electrons have a tendency to accumulate in the regions of lowest potential, and is also known as quantum well and located in the beneath on below side of the gallium nitride and aluminum gallium nitride. The ohmic conduct we are also use the ohmic conductors, that is source, gate and drain, introduced by photolithography. This is the image of photolithography. So it is from that image we can understand the epitaxial structure of the basic gallium nitride, basic aluminum gallium nitride or aluminum or gallium nitride high electron mobility transistors. This is data we measure from our motography equipment of our university. This is the graph. This is the figure of net positive charge between the how electron and photons are behaved in photolithography of the gallium nitride high electron mobility transistors. So last there is some active device, that is group 3 in a periodic table, group 3 and group 5 components, that is silicon and germanium. HBT, already I told HBT means heterostructure. heterostructure based transistors. So group 3 and 5 components HBC actually a modified version of BGT, bipolar junction transistors, with a wide band gap emitter and narrow band gap based regions. Due to their vertical current flow, HBTs can deliver excellent power density. However, because of substrate in gallium arsenide is poor thermal conductivity. So in between gallium, we are using some we are using some gallium arsenide substrate for our group 3 and group 5 components in periodic tables. So here this is the curve of silicon and germanium. Gallium have a diamond lattice structure, and the lattice constant of gallium is 4% greater than the silicon lattice constant. The emitter has a lower band gap than in the base, and although silicon germanium has a lower band gap with difference lattice constant. So another active device remains, that is silicon bipolar junction transistor and silicon CMOS. CMOS we know CMOS is most small size, and this is the less after BGT and FET, the CMOS is the most popular, and we are using CMOS in our IC design. That is CMOS actually used in our IC device, that in Cadence we are using the IC. We can fabricate IC or we can design IC with the help of Cadence. This one is used actually in CMOS, and gallium nitride and gallium arsenide is actually used in our simulation software ADS. We are using that's for our designing power amplifier, low noise amplifier, that type of device we are using here. So silicon bipolar junction can be fabricated with FET up to 25 GHz, and the potential in the fabrications for highly integrated circuit, which include not only bipolar transistor circuit but also by CMOS. The obtained silicon film has a higher electrons and hole mobilities, enabling higher drive current in CMOS transistors. The use of silicon CMOS technology ensures faster and more stable processing with higher productivity at a low cost. And this is the bipolar BGT bipolar junction transistor cross-sectional view of bipolar junction transistors. So this is the in front view of a bipolar junction transistors. Substrate P channel, source and drain are there, or in the middle between source and drain there is a gate voltage. Gate voltage used to control the P channel of the transistors. So now we can introduce the passive device of MMIC technology. So passive device means that is work for controlling something of MMIC technology, not directly used. So whenever we want to use the control of our device in micro monolithic integrated circuit, that time we introduce some passive components. First up we had the inductor. So everybody we know that an inductor is nothing but a coil of a circle of coil. So inductors can be realized using a straight narrow tracks and single ops electronics and multi-train spiral inductors. It is often used a distributed amplifier. The loop inductor was extensively used in monolithic micro-integrated circuit in the beginning due to the simplicity. However, the spiral inductor is now more widely used. Although the spiral conductor is easy to fabricate, it is one of the most difficult devices theoretically modeled because electromagnetic coupling between the metal is happening. So therefore the experimental characteristics usually is required also here. So this is our inductor. Some equations I already put. This one is inductors equation, this is capacitor equations, this is resistance, this is our transmission line. Looks like all of the passive components. Here I introduced the inductor. So the second is most important, this is capacitor. Capacitor play a good role in our MMIC design as a passive device. So capacitor, here capacitor MMI means micro electromagnetic capacitors. That is also metal inductor metal. So metal inductor metals means we know the capacitor is composed of metal and inductors. sorry, which has a high capacitance per unit area. An integrated capacitor can be used in MMIC. The capacitor is composed of two metal plates and separated by dielectric materials. This capacitor composed of two metal plates separated by dielectric materials. As I told, capacitor, two line between there, and this is a metal plate, and between the two metal plate there is a inductor layer which is separated the two metal layer. This one is actual the scenario of capacitor, and this configuration helps to minimize the fringing effect of the field to the ground and shorts between the upper and lower capacitor plates. So another one is resistor. Resistors is nothing but it is also impact on the designing as a passive components. Resistors are used as a feedback circuit and setting the bias point of active device, isolation and termination of power, combination of couplers. Two types of resistor are used in MMIC applications, that is including thin film of lossy metals and highly doped gallium arsenide active layer. So there is a major disadvantage are added in processing steps required to fabricate them, although thermal dissipations and difficulties and electromigration failures are also a concern issue of there. So this one is our wire, thin film wire. So in between thin film wire there is a resistance also exists. We know that there is a relationship between the length and cross sectional view with resistors. We know the resistors is equals to resistivity constant with is directly proportional to the length and inversely proportional to the area of the cross sectional. So another most important things as a in a MMIC technology as a passive components, so that is transmission line. Transmission line is nothing but a line between the source and load. That is actually when we generate, when we give the power between source to load, there is a line or cable is needed between the source and load. So this is actual the transmission line. Transmission lines and waveguide can be defined and device used to guide energy from source to load. Transmission lines can consist a set of conductors, dielectrics and combinations. The characteristic impedance of microstrips is inversely proportional to the ratio of the conductor and width and thickness of the substrate thickness, and also the electric constant of the substrates. So this one is our microstrip transmission line, and this one is the CPW line. CPW means coplanar waveguide transmission lines. These two lines are so much famous in our RF and microwave systems, that is microstrip transmission line and CPW coplanar waveguide transmission lines. So this is our actual feed line, and this is our the antenna or any materials when you used between this line. This is our RF line, and this is the actual cross section view of transmission line. So last one is combiners and dividers. Combiners are nothing but combiners are actually used to combine, from the name we understand, combine two things or more transmission lines into one transmission lines. So they also can be used to drive the microwave signal from transmission line into two or more transmission line. In power divisions, an input signals is divided by the coupler into two or more signals and laser power, and the couplers can be 3-port components with or without loss, and it can be 4-port component also. So these are the some combiners and dividers are there. So this one is combiner. Actually all transmission line RF characteristic RF line are comes together and combinedly make one line. That is actually we are used as 50 ohm transistor transmission line or RF line, actually used. This one is actual value of our characteristics impedance, and this one is our the we know the this one is so much famous in our gallium arsenide and gallium nitrate design, that is Wilson power divider rule. Wilkinson power divider rules, that is used also a combiners. Some passive components are there also. In some case we are using via and circulator, and also isolator we are used, and isolator allows a microwave signal to pass on directional but not in the others. circular routes and microwave signals from one port of the device to another port, and the arrow represents the direction of the magnetic fields and the signal when applied to any port of the device. And so another important things, we are used via hole. Via play lots of roles in our MMIC circuit design, MMIC circuit design, and via actually we need to give in our designing. So via holes are used in microelectronics to connect between two different layers. We connect from, suppose we need to connect from on routing line from third layer to fourth layer or first layer to second layer. That time we need to put via. Through the via, we need to connect this to routing line of this of our designing monolithical microwave integrated circuits. So this also play a vital role in our designings. So via actually in integrated circuit bulbs also it can be used electrically connect to both wire. Already I say silicon wafer we need to connect. So wafer means layer, one layer to another layer. We can also say. So there are many several reliability issues associated with via holes. If the via holes are completely filled with gold and cracking to the gallium arsenide due to gold and gallium, as the thermal expansion mismatch may occur also here. So this is the view of a via hole we are using here. Looks like upper level layer. This one is gallium arsenide layer and connect the ground plane. So we connect the ground plane and upper layer in between the gallium arsenide substrate layer. So we are using via. This is on its isolator. This one is circulator. So here it is circulator, it is isolator. So another things that is passive components are also we can tell. So that is metal air bridge, wire bonding, and bonding pads. So when we design on IC, so we need to connect routing line between this IC pad. So that time we need to do bonding. Bonding means to connect of this IC RF routings, IC route to our pad. So this is the connection between the IC route and pad. So an air bridge is simply metallic bridge that permits two transmission lines to occur cross over each other without of the formation of an electric circuit, short circuit. Bonds are provided to allow wire bonding for electric connections, though through the wire bondings and bonding pads. Already I told. DC bias can be supplied output signals and can be taken out. These bumps avoid the low pass characterization and the wire bonding connections. Series inductors and shunt capacitor also can be reduced by using the flip chip technology. So this is a metal bridge. This one is need to connect between this pad to another side pad in between gallium arsenide, and there is a transmission line also there. So these are the reference from where I collect some data for reviewing the reviewing chapter of MMIC technology books. That one is I mentioned here. So thank you for listening my presentations. That's of all. Thanks everyone.